In this video, we'll be using the ratio test as another test of convergence. So the first question people ask is when to use the ratio test. The ratio test is very useful when you have exponents that normally wouldn't be used in other tests, or if you have factorials. Factorials is a huge part of the ratio test. So the ratio test is defined as, so if you have the limit, you have the limit of, as n approaches infinity, of the absolute value of a to the n plus a of n plus 1, the n plus 1 term, so basically the next term over a of n. If it's less than 1, then we know that the series will be convergent. Conversely, if we take the limit of the absolute value of the next term over the first term, or the existing term, and it's greater than 1, or it goes to infinity, then the series, as you would probably guess, diverges. So if you have it equal to 1, if you have the limit as n approaches infinity for a n plus 1 over a n, and it equals to 1, then basically the ratio test is ineffective, and you need to use another convergence test. So basically the ratio test will be inconclusive in this case. So let's go to some examples. We'll start with an easy one. The first example is the series of n equals 1 to infinity of 2 to the n over n factorial. Right off the bat, because we see a factorial here, we can tell that we might need to use the ratio test. So if we hop right into that, we have the limit of n approaches infinity of the absolute value of, in this case, a of a n plus 1 would be this entire function here, but with, instead of n's, you have n plus 1's. So this becomes 2 to the n plus 1 power over n plus 1 factorial, all over the original one, which is 2 to the n over n factorial. And we want to know if it's convergent, then it will have to be less than 1. So let's use some algebraic manipulation to solve this. This will be solved as the limit as n approaches infinity. We can multiply both sides of the fraction, so we have a numerator here and a denominator on the bottom. If we multiply both sides by n factorial over 2 to the n, so basically times n factorial over 2 to the n, then the n factorial here will cancel out the n factorial here, and the 2 to the n will cancel out the 2 to the n there. Whoops. Then we can move it to the top. So basically what we'll have is an n factorial over an n plus 1 factorial times the 2 to the n will be on the denominator here, so we'll have 2 to the n plus 1 over 2 to the n. So basically, using exponent rules, we can tell that 2 to the n plus 1 would be 2 to the n times 2. I'll write it down here, 2 to the n times 2 to the 1. That's why you get 2 to the n plus 1. So if you divide that over 2 to the n, you'll cancel out both terms and you'll be left with 2. On the other hand, you have an n factorial over an n plus 1 factorial. Keep in mind that n plus 1 factorial is n plus 1 times n minus 1, and so on and so forth. So we can write n plus 1 factorial as n plus 1 times n factorial. So then n factorial will cancel out. Let me represent this here. So then these will cancel out, and you'll be left with a 1 over n plus 1 here. When we take the limit as n approaches infinity for 2 over n plus 1, we can immediately just replace n for infinity, and you'll get 2 over an infinitely large denominator, and that'll be 0. Since 0 is less than 1, then the series will converge. by the ratio test. And for our second example, we want to find the series of n equals 3 to infinity of ln n over n. Of course, ln n over n doesn't have any distinct exponents or factorials, but we're going to do that just for the sake of this video. We're going to use the ratio test. Using the ratio test, this becomes the limit as n approaches infinity of an plus 1. In this case will be ln of n plus 1 over n plus 1 over the original function, which is ln n over n. We can use basic algebraic manipulation to get all of these, to eliminate the complex fraction. So if we multiply both sides, the numerator and the denominator, by n over ln n, this becomes n over n plus 1 times ln of n plus 1 over ln of n. We want to find the limit as n approaches infinity of this, and it looks a little confusing, but using algebra we can find this pretty easily. So the limit of n approaches infinity of n over n plus 1 can be found using algebra. N over n plus 1 is merely 1 over 1 plus 1 over n, and if n approaches infinity, then you'll have 1 over 1 plus 0. So this basically becomes 1 over 1 or 1. And then we want to find the limit of, as n approaches infinity, of ln n plus 1 over ln n. In this case, we can use L'Hopital's rule, where we take the derivative of both sides. So the derivative of ln of n plus 1 would become 1 over n plus 1, and the derivative of ln n would be 1 over n, which is basically n over n plus 1, and we calculated that limit over here, which is 1. So basically, the limit will be equal to 1, and according to the root test, or the ratio test, the limit of the next term over the original term, if it's equal to 1, then it becomes inconclusive. So this is inconclusive by the ratio test. Thus, we need to use a different test. In this case, we'll be using the direct comparison test. It is most logical as we can compare ln n to a different function. I haven't really discussed much on other tests, but I'll definitely make videos on it. But the direct comparison test, which is another formula that should be memorized, we have an equals to ln of n over n. Basically, the direct comparison test states that if you have a smaller function and a larger function, the smaller function, if that diverges, the larger function diverges. And if you have the larger function converging, then the smaller function must converge. We think that it's most likely true that this function or this series will diverge because we have an n on the denominator and a smaller function on the numerator, but we don't know yet for sure. It's just a basic prediction. So we're going to try to compare this to something which is smaller than ln n over n. And a good one, since n starts from 3, we can compare this to 1 over n. Ln n is always larger than 1 when n is 3 or greater. So if we look at 1 over n, this is basically 1 over n to the 1. And by the p-series test, we can tell that the series diverges. And this is also a form of the harmonic series, which is basically 1 over n. And the harmonic series is proven to be divergent. So if 1 over n diverges and it's a smaller function than ln n over n, then we can say that the series will diverge. Not by the ratio test, by the direct comparison test. I'll abbreviate that right here. But it's still useful to know the ratio test. It is very useful in many different cases. And if it doesn't work, there are many other different convergence tests that you can use, and I proved that with this example.